Hi everyone, Mr. Sanford here. It is Monday, April 20th. It's about 4 o'clock, just after 4 o'clock. Working overtime on a Monday. Uh, Here to answer your questions or the questions that I gave you on ionic versus molecular compounds. Hopefully, you're able to understand what you read, that one-page document that I gave you. The main differences in terms of their structure are that those ionic compounds, remember, ions are charged atoms. So those ionic compounds are formed when a metal will give up some electrons, a nonmetal will accept or take those electrons, and together will form that ionic compound. And why do they do that? They want to give those electrons up or take those electrons in order to have a full outer shell. And that outer shell is called the valence shell. So that's a little review for ions that we looked at last week. We haven't really talked about molecular compounds yet, but the idea with those is that they are formed not by ions coming together, uh, so not by one giving and one taking electrons, but rather by sharing electrons. So they play a bit nicer. And those molecular compounds, if you saw the question that Alana asked in the comment section, those molecular compounds will be formed by elements that are that have more than one or two, or want to give away more than one or two electrons. So those are those ones that are in, group 4, group 5, sometimes group 3. Those will often be the ones that share electrons in order to gain a full outer shell. When they do share, so when electrons are shared, they act as though they belong to both. And we'll look more at molecular compounds later in the week or next week. But again, main differences: ionic compounds are formed by ions. Ions are charged atoms, either positive or negative. Negative because they accepted electrons, positive because they got rid of electrons. Whereas those molecular compounds are formed when electrons are shared in a type of bond called a covalent bond. Okay, so their properties. How do the melting points of ionic and molecular compounds compare with one another? Well, from the reading, you saw that the melting point of ionic compounds was far higher than the melting point of molecular compounds. So if I was to type that in, ionic compounds, that's that. Make that bold. So question 2, at room temperature, or around 20 degrees Celsius, what state are ionic compounds most likely to be in? What state are molecular compounds most likely to be in? So for ionic compounds, they're highly likely to be solid, right? So ionic will be solid. That's an identifying characteristic at room temperature. It's solid. It will be solid if it's ionic. If it's molecular, we're not sure, but could be solid, liquid, or gas. So it's more variable if it's a molecular compound. So we know that the ionic compounds have a higher melting point, but the more important question is why? So why do those ionic compounds have such a high melting point? It has to do with the attraction between the ions. So imagine a magnet, and you've got a positive side and a negative, or a north pole and a south pole, and those will attract. And once they come together, they're hard to pull apart. Well, you've got a positive ion called a cation, which is a metal, so something like sodium. You've got a negative ion, which is called an anion, which is a nonmetal, something like chlorine. And when those two opposites come together, they attract, and they're hard to pull apart. And you need to have a lot of energy in order to break those bonds, in order to get those ions further apart from one another. And remember, the difference between states is how far apart those atoms are and how fast they're moving. So when they're bonded together, they're solid and they're hard to move apart. You need a lot of energy. You need to crank up that heat. So when the temperature increases and increases and increases, you have to really get it hot in order to break those bonds apart. And now you've got those ions further apart, moving faster because you've added so much heat. So they've gone from a solid to a liquid. Whereas with those molecular compounds, since you don't have charged atoms, you don't have ions, in that case, they're not so tightly held together. So you don't have to apply as much energy in the form of heat in order to change their state from solid to liquid. So let me just summarize that here. So ionic compounds, high melting point, strong attraction, negative ions. Molecular compounds, lower melting point because less attraction. No opposite charges. Yeah. Okay. Electrical conductivity. So we're looking at, again, of course, we're looking at differences in ionic versus molecular compounds. So let's see here. How does electrical conductivity of ionic and molecular compounds compare with each other? So molecular compounds, let's start there. Molecular compounds have low electrical conductivity. And conductivity just refers to the ease with which electrons will flow through them, the ease with which electricity will flow through them. So molecular compounds, not so much. So those are things, and I should mention low electrical conductivity in any state. So something like sucrose, which is table sugar, not not particularly conductive at all, whether it's in solid, like I put in my coffee, or even when I melt it in my coffee, it doesn't increase the conductivity. Whereas with ionic compounds, it depends on the state. So solid has low conductivity. While liquid or aqueous has high conductivity. Aqueous just means dissolved in, usually in water. And of course, liquid means you've actually melted it. So by comparison to sucrose, which is table sugar, if we look at table salt, electricity will not easily pass through just a block of table salt. However, if you got it hot enough to melt that salt, which is very hot, I don't know what it is off the top of my head. Somebody can maybe look that up and put it in the comments. But if you got it, if you raise the temperature enough to turn that into liquid, it would be able to conduct electricity. Likewise, if I were to take that same salt and dissolve it in water, switch it around, it would now be a highly conductive liquid. So pure water, distilled water is not very conductive because it's not water is not an ionic compound. It is a polar molecule, but it's not a true ionic compound. So pure water, not actually a very good conductor. However, salt water, once you dissolve the salt in it, what you're doing is you're actually separating those, you're getting those ions floating freely in the water now. And all of a sudden, it does become an excellent conductor of electricity. All right, question 5. You find a white solid in a jar and decide to do some testing, find out whether it's ionic or molecular. What would you do, and how would you interpret the results to determine if it's ionic or molecular? Well, you could do a bunch of different things. So the simplest test might be, and if we were in class, we would actually do this as a demonstration, as a small little lab, where we put the fire to it. So you heat it up. And if we were in the lab setting, we would use Bunsen burners and we would heat up the substance. And if it started to melt pretty quickly when we crank the gas up on the Bunsen burner, that means the melting point is lower. So it's likely to be a molecular compound. If I put the Bunsen burner up as high as it possibly goes and nothing happens, well, then it's more likely to be an ionic compound. And that would be what would occur if we use salt versus sugar. That sugar would melt pretty quickly, and the whole room would be smelling of burnt sugar, and everyone in the science office would be mad at me. Um, but the salt wouldn't melt. As high as we could get the Bunsen burner, we wouldn't be able to melt that salt. So that's the simplest test. You could do some other ones with conductivity. Um, that's probably the easiest. Test melting point. If high, then ionic. If low, then molecular. All right, last one. Wax is a very common substance. Um, I've asked you here to, use your knowledge to try to figure out what type of compound it is, whether it's ionic or molecular. And again, if you were to just look at the answer to the last question, that should be able to give us a pretty good clue. So that wax that you use for your candles, it doesn't take a lot of heat. It's not super hot, the flame that's on the wick of the candle, but that is enough heat to melt it. So because of the low melting point, it would make sense that wax is molecular, which indeed it is. Oops. And that's it. So hopefully you actually try those questions before you see my answers. As I said, you don't need to submit your answers in the classroom as an assignment. You can if you'd like me to take another look at it. Um, but those are the main properties and the difference in properties between molecular and ionic compounds. So for the rest of this week, we're going to focus on ionic compounds this week, and we're going to look at how we name ionic compounds and determine formulas for ionic compounds. So we'll need to remember that stuff from the periodic table last week, what those groups mean, in order to help us not have to draw Bohr diagrams or not have to draw Lewis dot diagrams every single time we're going to figure out the formula for ionic compounds. So we're going to do that over the next few days, naming and formulas for ionic compounds. All right. I hope you had a good day and continue to have a good day into the night. That's it for now.